Hello, everyone, and thank you for joining our presentation for today. I am Hussam Alisa from Microsoft Data Center Advanced Development Team, along with my co-presenters.
I'm Robert Langston from Microsoft's Cloud Hardware Engineering Team.
And Brandon Rubenstein, the Director of Mechanical Engineering for Microsoft's Cloud Engineering Team.
Today, we will be giving an update on liquid cooling enablement for the Olympus rack using liquid-to-air rear door heat exchanger assist. One of the main objectives of OCP Advanced Cooling Solution work streams aims to streamline and standardize liquid cooling technologies. This session will be focused on cold plate enablement using air assist, with focus on enablement of liquid cooling in air-cooled dedicated and air-cooled optimized data centers. So what's driving the industry to liquid cooling or to require cold plates for their chipset? So what we're seeing is an increased chip fluxes, whether it's CPUs and GPUs and accelerators in general. The chart to the upper left shows CPU power and T-case requirement for different CPU generations. The blue column represents power, and the orange represents T-case required. We can see that across CPU generations, power is increasing. Could be number of cores increasing or other features are added to the chip. Similarly, looking at the GPU charts, power has been going up constantly. And sometimes it is possible to have the power increase accompanied with a reduction in the required T-case due to power increase or die size shrinking, etc., which makes the thermal solution more challenging. There has been a lot of work, though, and an investment into optimizing air-cooled data centers. So as we move from chiller-cooled DCs with higher mechanical overhead to introducing economizer data center and free air-cooled data center, PUE has been going down, as well as water consumption, as well as cost. So this shows that there has been a lot of effort into optimizing air-cooled data center on the mega scale. But in the light of the fact that most of current hyperscale data center have been optimized to run efficiently using air-cooled, and when we require to apply liquid cooling into them, we have to be cognizant of the fact that not all the applications might require those higher flux chips for liquid cooling. And we might end up with mixed low flux and high flux chips based on racks throughout the facility. So we need to make sensible TCO-driven decisions. Do we need water throughout the data center or locally, which could be retrofits that can be rather costly or disruptive, or what we will be showing you here today, which is the use of air assist water cooling. In the next couple of slides, we will share some case studies we ran on compute and GPUs using liquid cooling. Here we are showing a case study on the Olympus compute server. As you can see, the conversion of the air-cooled Olympus server to a hybrid cooled or a cold plate-based liquid cooled server is pretty seamless, which involves fans removed, tubing added. The fan speed will auto-modulate, reducing the server power. And this shows that we can do a rather quick enablement for higher chip flux that might prove to be challenging to air cool. The chart to the left shows a comparison between CPU temperature running air cooling at 35 Celsius inlet versus cold plates across a sweep of water temperatures. The gray bars show the air-cooled CPU junction temperature versus the colored bars showing liquid-cooled CPUs across the sweep of ASHRAE W1 to W4. The uber point here is that the use of liquid cooling enables us to make decisions such as run with colder water temperatures, potential to take a hit on efficiency, but an enabler for further chip performance. So there's a trade-off to be made here. Another option would be to run warmer water, enable infrastructure efficiency gains such as dry coolers, etc., and still potentially run colder than a case of air-cooled solution. One thing to point out, though, in this slide that there was, as you can see, there are cold plate or liquid-cooled modules almost on most of the components, CPUs, DMF, M.2s, and FPGAs. And this affects the heat pickup ratio between the air and the liquid. But in reality, that decision has also to be TCO driven, taking into account the power reduction because the fan's ramping down further. However, we need to take into account the effect of the added cost for the extra modules. This is another case study we ran on our Olympus expansion chassis, HGX1, which is a server with 8 GPUs. The air-cooled chassis was running using 3 UTOL heatsink solution, while the liquid-cooled has been retrofitted with 8 cold plates. This study was a collaboration across the server, software, hardware, and GPU teams, as well as externally with CoolIT, ZT Systems, and Ingrace Systems. Similar to the CPU case, so we ran an investigation whilst running neural network type workloads provided by Microsoft GPU team. In both charts, light blue and yellow columns represent the air-cooled permutations for cases of 35 Celsius and 25 Celsius air respectively. Orange, dark blue, and gray bars show data points for the water temperature sweep. The server power consumption graph shows that the effect of reduced server power when using liquid cooling due significant fan speed reduction and reduced leakage current. While the average GPU performance chart showed an increase of performance with colder temperature. Again, this brings up the decision that liquid cooling enables, which is running colder or warmer water and taking into account the trade-off of infrastructure versus chip performance. Okay, so the previous examples were case studies on retrofits, meaning air-cooled servers and chips transformed into liquid cooling for sensitivity analysis. But such studies encourage building chips that are higher power or higher performance and requires liquid cooling from the get-go. So the big question we are trying to address here, how can we enable liquid cooling for higher flux chips in data centers that where facility water is not present? In the session titled Air-Assisted Liquid Cooling, Cold Plate Enablement in Air-Cooled Facilities, air-assisted liquid cooling options were discussed. Here we will have a deeper dive into the Olympus rear door heat exchanger system. As you can see in the left most figure, that shows the Olympus rack with a rear door heat exchanger and N+1 fan configuration. Looking inside the rack with the rear door heat exchanger open and the rack empty of servers, you can see the Olympus rack PMDU for BlindMate power, but you can also see the right BlindMate manifold for BlindMate cooling. Ease of services is an important aspect as well, as you can see in the right and the clip to the rightmost, where enabling BlindMate power and cooling in play facilitates serviceability. Next, Robert will walk you through details of the Olympus rear door heat exchanger system.
As Sam mentioned, the goal behind the air-assisted liquid cooled rack is to provide an open-loop liquid cooling levels of performance in an air-cooled data center in order to enable higher heat flux chips. This is accomplished by using a rack-sized heat exchanger and centralized pumping system to maximize performance and efficiency. The liquid heat pickup ratio can vary depending on server design, where certain percentages of the heat is circulated through the liquid loop to the rear door heat exchanger, where the remaining server heat is picked up by the air flowing through the server in a more traditional air-cooled fashion. Ultimately, 100% of the server heat is rejected into the facility air. The solution is being designed to cool up to 40 kilowatt rack with less than 5% cooling overhead and an airflow consumption of less than 145 CFM per kilowatt. It's intended to be both Olympus rack and ORV3 compatible. The rear door heat exchanger is designed to fit the 48U Olympus rack and be compatible with the OCP rear door specification. It uses 5 hot swappable 280 millimeter axial fans capable of up to 4,800 CFM. There's a mounting bracket which provides the interface between the door and the rack and allows for easy replacement of the rear door if needed. This mounting bracket can be changed to allow for compatibility with either the Olympus rack or the open rack. The current POC system has a standalone control system for the door. However, future iterations should interface with the pumping unit to allow for external control and management of fans. Telemetry from the door includes differential pressure, air inlet, and individual fan, tach, and control signals. The fluid distribution manifold is designed to mount on the rear of the Olympus rack and provide a blind mate interface for up to 42 1U Olympus servers. It uses Stobleed CGD03 blind mate connectors to the servers and CGB20 manual mate dry brake connections for the inlet and outlet fluid. It also incorporates an automatic air bleed valve. In the future, the manifold and quick disconnects could be modified based on server requirements. For example, to support servers of different U heights. Additionally, it could be converted to use standardized quick disconnects once available. Microsoft and Facebook have been collaborating on a common specification for the reservoir and pumping unit. The specification is discussed in greater detail in the air-assisted liquid cooling, cold plate enablement, and air-cooled facilities thread. But it is intended to be compatible with both Olympus and open rack designs and can support various methods of air-assisted liquid cooling. The design uses redundant custom GRI pumps with maximum one pump performance of 50 liters per minute at 25 PSI. The pumps are fixed in the current POC, but we are driving for hot swappability in future iterations. The system can monitor supply and return pressures and temperature, as well as flow rate and pump speed. The RPU will interface with the rear door heat exchanger to manage and monitor its differential pressure and fan speed as well. The internal control system will vary pump and rear door fan speeds to maintain defined operating conditions such as flow rate and temperature. It will also interface with a rack level management system to allow for external monitoring and adjustment of operating conditions. The control system in the RPU will allow for the liquid cooling system to be used across a broad range of platforms and use cases. Operating conditions can be adjusted for each platform to allow for optimal system performance. For example, here we show how two 40 kilowatt racks with varying heat pickup ratios can be adjusted for either efficient operation or to maximize cooling performance. By increasing the supply water temperature by about 4 degrees C, the required rack airflow rate and cooling power overhead can be greatly reduced. Although there's still a lot of testing to be done in this initial POC, there are several improvements and optimizations that we would like to drive into future iterations of the design. We need to implement hot swappable pumps in the RPU to improve service and minimize service downtime. We need to develop the control systems for the RPU to manage pumps and fans and external communication paths for monitoring and management. We think there may be opportunity to optimize door coils and fans to improve performance and minimize the impact of fan failures. Finally, we need to identify multiple sources of pumps that meet the RPU requirements to ensure supply chain integrity.
So thanks, guys, for all the excellent work that went into the presentation and all the work that went into the investigations. I think the big overarching message here is that we're committed to the liquid cooling solution in an open platform, but we need assistance. So this slide is dedicated to some of those concerns. So in order to develop at the scale and the cost that we need standardization of specification and interfaces. So all the components need to be standardized. They need to fit together. They need to be somewhat commoditized: rear door heat exchanger, manifold, RPUs, pumps, and coolants. We need consistent guidelines for deployment, serviceability, and control, so that different sources have uniform means of upkeep and deployment for these systems. Vendor and end user collaboration on monitoring is a key to integration into the overall platform and infrastructure. So without that, it really is a custom solution, even if the hardware looks identical, and again adds to the difficulty in scale deployment. And finally, leakage and risk mitigation needs to be standardized, again, for the standardized interface into the infrastructure to minimize the effort of scale deployment. So to close out, thank you for watching and listening to our presentation.